So hello, we'll wait for the others to join and then we'll start. Yeah, meanwhile, you could maybe try to identify yourself a little bit of those who are joining today for the workshop. Be nice to see who we have today. I'm expecting to see some of the students who are doing the research work with me, maybe some others, so please let me know who you are here. Oh, I just realized that the chat is disabled, so how can I enable chat? Just a second. It was interesting that I cannot do this. Why? Just a second. There is something strange going on. Just a second. Yeah, finally. Now I will have the chat. Just a second. Okay. So I should enable chat now. Yes. So we're back now. So yeah, if you refresh, you should get the chat messages. Okay. So we have chat back. So say hello. Apparently, if you set that the video is safe for children, then YouTube do not allow to use the chat function. Can you see the chat? Can you see the live chat? Plus, minus. Yes, 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 yes. We have some action going on. We have 9 people online. Yeah, please say hello. Let us know that we are live. Okay, it's going to be quite an interesting session today. Great. I see 1, 2, 3, 4. About like 4 people identified themselves, and then there are 8 people to total. So 4 mysterious ones. Okay, that's fine. So yeah, I'll listen too. So in if you go to the Google Classroom, so Classroom Google, just a second, let me flip around some things. So you should find there just in a second the template for today's session. It will be 14.2, the workshop assignment. So I'm assigning it now. 14.2, right. So let me show you where you should look. So here, if you go in your classroom and find 14.2, that should give you the template, Variational Autoencoder template, and the encoder PNG file. That is the task of creating the encoder. So before doing that, I will give some brief intro, but meanwhile, please copy these files and make sure that you can open them. So that's number 1. Number two, we will start explaining about the actual variational autoencoders. So some of you did successfully make the simple autoencoders and denoising autoencoders, where you have the input image, and these are unsupervised learning. So that means that you don't need any labels, and it can learn all sorts of great stuff, like children do. For example, they also don't have a lot of times the labels, but they can understand the world. So this one is the input, and this one is the output. And we can train that with, for example, mean square error. And remember that in the simple autoencoder, we had this encoder producing the z vectors here, and then we get out the decoder path. So the simple autoencoder can be used for many things. For example, pre-training some kind of like classifiers or anomaly detection to detect something that is happening unusual, or to cluster some data to make unstructured data structured. So in this kind of model, variational autoencoder is considered actually, I think, the first truly generative model that we will make. You know the very famous GANs, right? GANs, right? So those are the famous models that where you can generate all sorts of interesting things with without defining specific distribution that you would like to train to. So this kind of model will allow you, when you train all of this thing together, then later you can use only this part and sample some z vectors and generate new content. So basically you could create something that is creative, you know, like you can generate letters with larger lines, with smaller lines, maybe if there's colors with different colors and all sorts of things. And in order to do that, we will create these two variables here, the standard deviation or sigma, and mu or the mean value. And then we will plug those two values inside the normal distribution and sample out of normal distribution the bell-shaped distribution, some vector that will be multidimensional, let's say 32 dimensions, and then we'll generate this part. So I will show you how to do that. So there is a question on the chat. I have a question about when to save the model. When should you save it? When can you know that you have the best possible loss? So you should save it with regards to different metrics, the metrics that you apply on the test data set. Remember that we always track two metrics, at least two. So the third one is after you've completed the training, then there is a validation set. But you have primarily two metrics, the train loss and test loss. So if we think about, so this is a question from the chat, that's why I'm talking about this now. So that is advantage of being online, so you can basically ask questions. So imagine that this will be the loss, right? So you would like to see loss something like that, right? So let's write that the red one is train loss, right? This one going to be the red, right? And then we also, so this is one of the ways how you can save the best model. It's just based on your loss function, but you can do also for other metrics as well. So, and for example, maybe at a different scale, maybe not even with the same scale, you would have the test loss that would go a similar way, but it will start going up at some moment, right? So remember that this moment when the loss goes up, it's called in this very specific term. Can any of you recall the term? What is the term of this situation? Like, if you can like type in chat if you remember. If not, then so what is this called? If you don't know what it is called, then type in minus. So then that would also help me to understand what you understand and not. So if we let me plot a little bit the line. So here we'll have the epochs on the x-axis. And so we have some ideas coming in. So epochs and the loss, right? And what do you think? At what moment should you save your model? So at what moment it would be good to save the model? So yeah, that's right. I'm happy that you know the term of overfitting. So the overfitting would happen if you would be in the location here, like after actually where the test loss starts growing. But at what moment, basically, what do you think should be good time to save the model? Yeah, so about the idea that the test loss is better than the previous one, it's maybe not. So the loss usually don't go like this. It usually have a lot of these jumps, right? It goes like this probably. So you should always have some kind of smoothing or like some, what else, some kind of steps that you take in account, some window. But basically you would like to save your model somewhere like in between before this happens. So you basically you can never tell when this exactly happens, but it would be great if you can save the model sometime when you would have the best like the minimal test and minimal train loss. At that moment you would save your model. So this is just one way how to look at it. You can look the same way with an accuracy, with something else. When the test loss is consistent with some specific set of epochs, maybe yes, but the most important thing, you don't want the test loss to start growing, you know. You don't want, so at this moment, when the overfit happens, the model is starting to memorize every single element, every single sample in your trained dataset. This is totally not beneficial, because if your model learns every sample of the training set, it don't learn actually the generic features that are also found in the test set. So that's why. So that was a little thing off the topic because there was a question about that. But let's return to the variational autoencoders. So let me show some of the features that you get with variational autoencoders. So one is that you, in this embedding space, because of the constraint of the distribution that you want the model to learn, you have the option to, so basically the model, after it converges, it will have some kind of semantic meaning inside the embeddings. So here you have the your embedding vectors of many samples displayed in dimension reduction algorithm, probably PCA, where you see that different samples of different classes kind of arrange themselves without telling anything to the model in some kind of order, where you see that similar letters are closer together, like zeros and 6, zeros and 8s, 9 and 7. Here, let's say 1 is quite unique. Then the 6 and 5 closer, right? 8 and 3 very close. So basically you get this effect for free. And this is great because you can also encode not only different classes, you can encode different styles and all sorts of things. And this is all created without any engineering of your side, except the loss functions, except the prior distribution that you choose. So for the variational autoencoders, there are different kinds of distributions you would like to use most likely you would like to use the Gaussian normal distribution. Then the other thing that you can do that I think it's quite fun, you can do that also with the other generative models, probably GANs and things, is that you can do the vector math, the vector arithmetics with the embeddings. So for example, if you would have, let's say, what you could do, 9 embedding of the 9 and the embedding of the 3, and you would create the average value of those two embeddings, that would be constitute basically to having as a plus arithmetic, then you would get 8 most likely. So the same thing if you would train these variational autoencoders or GANs on human faces, you could do something like smiling woman minus neutral woman plus neutral man, and you get smiling man. And you get this again for free. There's no like specific way how you manipulate these embeddings. This is just the fitting to the normal distribution or some other distribution or some undefined distribution also. That is possible to do sometimes. So then another example, you can so if you find some specific style of the let's say the vector, so if there is some numbers, some zeros that are with a thin line and with thick line in your dataset, and you take all of the samples with thick lines and you calculate the average of those vectors, and then subtract it from the all zeros, and then apply this kind of thickening style vector by average or just by addition to some other number, let's say 7 or some other number, you will get this number with this style that you selected before. And the same way you can manipulate like those embeddings and find, like with the glasses and the mustache and all sorts of things with the faces. Again, I must repeat that all of these operations are done after you have trained your model. This is not something that you train model specifically to do, but when you have trained your model, you have the capability of encoding and decoding those latent vectors and manipulate them and create all sorts of useful things. So this is one way how to operate with them. The last example why this is a good model is basically with regards to identification. So any model that is capable of creating latent space that is homogeneous and containing semantic information, you could use also for re-identification tasks and let's say something like zero-shot learning. So you can have the samples of some person here or here or here, like these are enrollment samples. So you pass through your encoder all of these images, you get a bunch of latent vectors, and then you calculate the average of those vectors or just use all of them as they are. And then you have some kind of query vector. So the query vector is just, let's say you have a new video that was not related to the enrollment video, and you can match up which is the most likely candidate for that query, and you get out all of these samples that they are basically from that pool the most likely candidate, and then you can match all of this same person with some of the enrollment samples. So actually in this case this is a training set, but it could be also enrollment samples. So then you can match which person is it from your enrollment samples, and all of this, again, all of these operations are not done during the training time. So you can do these things after you train the model. So if you have a model with different kind of people, with different kind of faces or different kind of articles, so then you can, when you train it, you can apply it in some zero-shot learning fashion for re-identification. So you can imagine this is the way how most likely Apple ID and all sorts of identification systems work that don't require you to retrain them every time you use them. So I hope that's clear so far. Let's double check. So is it clear why variational autoencoders are cool? So let me know. So plus, minus, if you have some question, let me know, and then we'll start coding them. Actually, before starting coding them, I will need to explain a few more things, but we'll get to coding very soon. Maybe you already fall asleep. No, I got 3 pluses. Good. Let's hopefully, if somebody posts a minus, then also good. Then at least I would be good. So sounds like magic. Funny. That's good comment. So I mean, you will see why it works. You will see why it works. So the next part. So before we start coding it, we need to understand the architecture of it a little bit and the loss function, definitely. So this is good picture of the model. So here in the the encoder part, we have the same encoder as for the simple denoising autoencoder. Then the decoder part again, the same way. And here, when we have this was the z vector at this place that we had for the simple encoder, but we will pass it to the 2 separate linear layers, linear projections. Basically, we project this z to 2 different ways. Also, you could even have 2 different sub-models here, some small multi-layer neural networks. And you produce 2 scalar values. These 2 scalar values are the same dimension as the z here. So 32 dimension vector u and 32 dimension vector standard deviation. And then we apply some trick to enforce this sampling effect, basically to make sampling operation tractable, so we can pass the backprop and the gradient of error through all of these things, and then we generate it back. And here in this part is the equation that is kind of important, but we'll look at that a little bit more in a second. So about that part of the equation, what's important is following. So we might not need that equation if we do things very inefficiently. If we do our model like in a very resource inefficient way, then we can actually not do this this part of the equation. So if you look at this small graph here, so there is an encoder and there is a decoder. So these are convolutions network, and here is the transposed convolutions network, or some kind of other decoder where you have upsampling methods. Now, when we go through the encoder model, we could create this, let's say, mu sigma, or even we could create just z, and we could generate all of these things like, so normally what we could do is not to create the mu and sigma, but just to create z and pass this part, the middle part, like, I don't know, like thousands of times, and then calculate what is our standard deviation with regards to z, and what is our mean value from all of our z's. We have 1,000 z's now, and what will be those values? And then we can, for example, calculate back the error through all of those 1,000 samples that would not be like feasible to store in the memory, and then fit it to the normal distribution. So you see here there is actually n normal distribution, the Gaussian, and then try to fit that the z vector follows the normal distribution. So if you remember, normal distribution was, let me check. So yeah, I will let you know about reparameterization also in a second. So let me see. So normal distribution, I forgot about the picture of that one to include in presentation, but that's going to be quick, I think. So if you remember that the equation is following, and depending on the parameters, you get these bell curves. So basically, let me put them here. Okay, so this is one of the bell curve ways how you could do that, but depending on the parameters, there should be, oh man. I will answer the question about reparameterization in a second. So reparameterization would be a method to avoid having this way that you need to call your model like thousands of times and then do the backprop through all of those thousands of times to calculate this mean and standard deviation. So what you want to do actually is to fit the z vector so that your z vector follows one of these lines. So on these lines you choose yourself. So in most cases you would use the mean of 0 and the standard deviation of 1. So that would be the red line here in this graph. So that is most common, like the prior distribution that you want to enforce on your z vector. So what it actually means is that you want your z vector to follow this normal distribution of this red line, so that if we go back one slide, that let's say the numbers in this data set, their similarity is somehow related to the similarity of, so between, like, so that it would be distributed by this normal distribution. So if you would like to have very like unique samples, like in very tight clusters, then you would maybe want to have higher amplitude in this distribution, like so to have these samples closer to 0 and not so like flat curve, you know. So that is something you can control actually. So, but again, to not call this like a model like thousands of times, there is a reparameterization trick. So it's called Reparameterization Trick, and the trick is following: that you have learnable mu and learnable sigma, and you have not learnable epsilon here, the random node. So, and this not learnable epsilon is sampled from this red line, from this normal distribution, just a very simple dumb sampling, and then you multiply it with the sigma here and add the mu. And what it actually happens is that every time when you call your model for the training purposes, is that you would have different kind of constant here. And if you remember derivatives, that if you have the constant, that doesn't change anything. If you multiply something by the constant, it doesn't care. So you can pass the gradient through and go to the next part. So this is the way, with this very simple, very small equation, how to simulate the effect of the like the distribution that it learns in itself, without need to call many times this model to calculate the actual mean and standard deviation and then do the backprop so that the model learns the actual mean and standard deviation. So you can do this just by calling every time the model and then do the backprop for every time. So it will make more sense just in a second when we look at the loss function as well. So let me see if I add a little, so how to transparent, so just a little bit red. So this is important stuff. So in your forward pass you will need to implement this thing as well. So the last thing missing, I think, is the loss function. if I'm not mistaken, if I not left out something else already. So for the loss function, we use two things. So let me give you the final loss function, and then I will go a little bit back. So this will be also a very interesting type of the loss function. So this is a composite loss function. This is, I think, the first proper composite loss function that we use. So there are two loss functions in the one loss function. So the mean square error that we know very well, and then there is the KL part. So this is a so let me not mistakenly pronounce it. I think always KL divergence, but they always say it without the full name. Kullback-Leibler. So maybe I will also add this name here. So I'm not a native speaker, so sorry for that. So yeah, so this is the KL part, and I will just explain also that one. So the motivation for the KL is just fitting that distribution to that Z. So one way to look at it is that KL will be 0 when the Z vector will have exactly this kind of distribution. So that all numbers in the Z vector, if you look at them, you will get a distribution that is something like that. And so there is two opposing forces. This is similar like in the GANs. You have the mean square error that is trying to get the output right, and then there is KL who is trying to eliminate the correct output. It is trying to make that your Z vector is always the same, always the normal distribution. And in order to bypass that is the only way that you need to fine-tune your parameters, the B, like the beta here, and also the learning rate and other things, so that at some point the only way forward would be to increase a little bit KL loss and decrease this mean square error loss. So maybe I will find some sample of that. So the nature of the loss function is very different to something that we've seen before. Is that, so this will also be from one paper. So if you just look at KL part, you will see that in the beginning, the KL part goes down. So in this image, actually, it kind of stays the same, but it usually goes a little bit down and then sticks to to 0. And then at some moment, during your training iterations, at some epoch, the KL loss will start grow. And this is counterintuitive because normally your loss should go down, but here the mean square error loss will go down, but KL at some moment will start going up. And the interesting thing what will happen is that it will start deviating from the normal distribution just small enough so that you would get some useful information through this latent space. And in order to do, when you do that, you will get really great effects because, let's see here. So in this picture it shows that depending on beta value, by the way, depending on the way how you calculate either this is a mean value, sum value, or some other way, this beta can be not only 150, it can be 0.1, it can be 0.01 and something like that. It is highly dependent on the way how big is what is your ratio between this part and this part. So it's not always like that. But the idea still holds that you can see here, you have a specific data set where you have small ball, and this small ball is going in the y direction and the x direction. So if you have if these two parts are very similar, basically if the loss of these two parts are similar, then you would get very entangled presentation where at the end it uses all of the dimensions. So in this case, the idea is that here you have the dimensional z vector. So how many dimensions we have? 1, 2, 3, 4, 5, 6, 7, 8 dimensional z vector. And when you have the ratio between this part and this part equal, then you get z vector that is quite messy. But if you have quite strong KL divergence, so that it suppresses this part very much, then you get a very interesting effect where your model actually use only, in this case, 4 dimensions of all of these. So I'm not sure if I'm interpreting this correctly, but basically here I think only the 2 dimensions actually it will use. If I'm not sure about these 2 first lines, it seems like that actually this is original input, this is reconstruction, and it actually you have 6-dimensional z vector, and it uses only 2 dimensions. And if you look carefully, this is very important, that all of these other 4 dimensions have very similar output, right? So, and this is because it is trying to fit that normal distribution and don't do anything useful with your, like, with these dimensions. So there is a lot of information so far. There is still missing some pieces. Let me show the last pieces, and then maybe you can ask some questions. So the KL itself, is, you can apply that to any distribution, not only to the Gaussian distribution, to the normal distribution. So there are, depending on the way what you input in the equation first. So first of all, you actually can use that also for classification tasks for some specific cases, especially where you have so you would use that when you have the ground truth of classification, something like for the 3-dimensional vector, something like this. So remember that normally in classification we always had only one class that we want to find. If you have like 2 labels with some kind of probabilities that are not actually like 100% just one of the labels, then you cannot use actually the categorical cross entropy, and you should use then the KL. But KL can be used in many ways. So you can also insert here the P as your model output and Q as some kind of prior distribution. So it could be Gaussian, it could be uniform, it could be beta alpha distribution, it could be Gaussian distribution. There could be all sorts of distributions. And also it is important in what order do you put it, P and Q, what order. So depending on the order, if you put P first or P last, you will get different kind of fittings. So here the KL is 0 when this is fitted to some part of PZ here in this manner. So if you don't want this to be average of any PZs, but just with the 1 dimension to be fit here, so you can imagine that first dimension fits this one, the second dimension fits this one, and the third dimension fits some other part of the distribution. So that's quite beneficial. So actually variational autoencoders use this one. So the last piece that is missing, I think, is that we need to put inside this equation the normal distribution. So if we put in the Gaussian equation in this one, at the end we would get the same equation that was in the previous slide. So if I go back here, see, this is the normal distribution equation, right? And if I put that one inside here, and basically 2 times, I put here the normal distribution and here, one of the normal distributions are produced by my model, another one is my prior that I want this to be fitted to, then I get these loss functions basically. So is it clear so far or not? Is it clear? So plus, minus, and maybe ask question in the what exactly not clear, and then we'll finally start coding this thing. Hopefully by let's say 30 minutes or so, we will start running this on Google Colab and see some nice results. Meanwhile, while I'm waiting for your answers, I will try to find maybe some other image of the loss curves from one of my experiments that I did before. Actually, I recently did the CC beta variational autoencoder GitHub. That was quite really cool stuff. Let me see, CC beta. So that I did not find in Pytorch that implementation, so I made it myself. So you can find that in GitHub, but I will try to find some of the nice loss functions that I had there. Maybe I will give you also for the homework some interesting data sets. So let me add some pictures more here. I see that in chat you say that it's difficult to digest. I agree. If you see this first time, it's not easy to understand, but I hope that you will have all information needed. So here, normally in the very beginning of the training, it quickly fits to something like this, where you see like the output is always the same for any of the letters. And then when you train it more, you start getting out these like shapes. And it just means that it is here it's fitted to normal distribution, and here they are actually breaking out of the normal distribution. And the loss lines, the loss curves actually looks like, let me find you. So here's another example from another dataset that I did. So this is one of my synthetic datasets that I can share you later. So there are like different color balls moving around the image with different sizes, and you can see that here the reconstruction loss. So the reconstruction loss is, let me see which one are those. So I guess these are the reconstruction losses. So it's going down, and the KL loss, it's starting to go down, and then it starts to go up, and then this is a really beautiful thing. So it's actually when it went up, it starts going again down, and then at some moment it will start go again up. So you need to catch the right moment. But so the idea is that it tries to get out some information through that bottleneck, and then it starts encoding it back down, and then again. So this is like a fight between those two losses to encode the minimal amount of information needed to do the reconstruction. So what you have there? There's a question more. I'm not sure I understand the KL divergence. Why are some balls more white and some less? Not sure about that part. Why one has 4 red color peaks and other have 2? So this data set is not related to the letters that you see before. So this is again different data set, but I wanted to show you this these curves of loss functions. Hopefully today you also see those curves. And KL, what are those weird U and B, how they are calculated? Let's look what you mean by U and B. U and B. So here you have the B. This is the constant that you choose as a hyperparameter to regulate how strong you want your KL divergence to be enforced. So here there is a strong enforcement, and here there is a weak enforcement. And I'm not sure about you. So you mean the mu, this one, right? So this is something that you produce inside your model as just a vector from the projection inside your model. I will show you how to do this in a moment. And this is also what you do there. So, okay, let's move to the coding then. Been talking for a very long time. It's really hard to explain it quickly. So, if we go back to the code, so I gave you the template. I hope you already got it. So here we have the to-do to create the encoder. So you already have the schema. So how to do it, right? You have the schema. So I will add it also on the 7th slide. So please, when you have done it, submit the assignment, so I know that it's finished, and then we'll move on to the decoder part, and then we'll move to the loss function and the middle part of the model. I think that's going to be, I will show you those things, but in general, a lot of things you can do yourself at this moment. There are only very few things that you don't know how to do, and those few things I will help you out. So even though it looks like really hard or stuff like that, but it's not really hard. So let me find this thing. So again, the encoder, unfortunately, is in this format, like very large sausage. Cannot really show you in detail, so you need to open that image yourself in some image like viewer and carefully code it. So let me check if somebody already did the encoder. If I will start coding it as well slowly, so you should be able to do this yourself definitely. This is something that we did with the convolution models and like with the autoencoders. This has been done many times already. So I'm opening it. Yes, that's good. So I will start showing how to do this as well. Let me check, no questions. Okay. So the encoder part should be easy one. So torch, let me zoom in a little bit. Torch NN, convolution 2D. Just a second. So convolution 2D, the in channels, because this is a grayscale image. If I give you as a homework that dataset with the color balls, then you would have 3 color inputs. So out channels 4, kernel size 5. So let me think about this a little bit. So what we have there? So I think the other parameters should be as default probably. That's why I didn't give them, but we'll check that out in a second. And then maybe I will double check it myself before. Just a second. Need to make sure that the other parameters should be default most likely. So just a second. You can actually like code all of the other parts as well, like right now, but I will double check this case where in the schema there are some parameters missing. I think they should be default ones. Yeah, so they should be default ones. Then the next layer is relu, of course. Torch and relu. By the way, I will. So I'm okay that you like a little bit change the thing. So I will add the leaky relu. So it's a little bit like better for the vanishing gradient, specifically when you don't have skip connections at all. You know, when you have skip connections, then leaky relu like not so important. But without skip connections, this is a little bit important. So then the next one. If I would make a state-of-the-art model, I would use the group norm, but in our schema there is a batch norm. So let's use the batch norm, and we have quite small images, so that also means that we can pass enough of them to have proper batch norm working. If we cannot pass enough of them, then definitely not good idea to use batch norm. So if you have 2 samples per batch, this is like very bad idea to use batch norm, even like 8 or 16. So 4, 8 out, padding 1. I mean, what is this? So again, this schema could be much better, I think, because now the kernel kernel size. Where is the kernel is 4, right? Very interesting arrangement actually. Padding 1, stride 2. So we are reducing the size without the pooling operations. Again, not the kind of the way how you would do this with the state-of-art models, but still good to understand these things. So here the 8. So 8, 8, 8. Then again we'll have the convolution. So we want to reduce the size to the 32 dimensions. So the 8, 8, 8, 8, out 8, kernel 7. What are the default parameters? It was, let's check. So the padding 0, stride 1. So the default parameters would be padding 0, stride 1, but just to not confuse, I will leave them out. So then again, the leaky relu, or relu, it doesn't matter at this moment much. I don't suspect that it will give huge impact on the performance. Then we'll have the, what we have here, so let's see, 8 to 16. Yeah, 8 to 16. 8 to 16 and kernel size of 4, padding 1, stride 2. Then again the relu and batch norm to the 16, batch norm 16. Then again 1 layer without changing things. 1 layer without changing things, it seems like. Except the width and height will change, I guess. So here the 16 input, the kernel size 4, padding, the stride 1. Very unusual architecture. I don't remember when did I make it, or some student made this for me, but still we can try out, it should work. So then the 16, okay, convolution again. This will raise it to the 32 dimensions of the channels. 4, padding stride 2. Then relu, then batch norm of the 32 dimensions. And then basically maybe we can add something that would be beneficial. Let me think. So if we fit it to the normal distribution of that one, so yeah, you should get this to this far. I will think about it. Maybe we can add something to improve the performance. So if I add a breakpoint here, and I just want to double check that my size is correct. So if I run it with a debugger, so I know that some of the students were not running the code with the debugger. That's really hard, I think. So you should prepare the debugger, because especially for the Pytorch, debugger is beautiful, you know. You can look inside your function graphs and stuff like that. You don't need to prepare everything beforehand as it is with the TensorFlow. So here I actually saw that the output is what we want, 64 batch size, 32 dimensions, 1 by 1. That is excellent. So that means that I don't have a bug. So if you add a breakpoint on line here on the Z and look what you have in the out and out flat, and if it's a 32 dimensional vector, then you did your job correctly. If not, you need to fix your encoder. So I see 2 people handed in encoder. That is beautiful. So I will open also decoder task. So you can start coding the decoder as well, and I will do that as well. So I am opening decoder now. So the task 14.23 with the decoder is also opened. And I will add that one as well, just in case, in the 7th slide. But you should look at that in the classroom. I think that would be better. So that we have there. So yeah, meanwhile you catch up with the decoder, and I will also code the decoder. If you have some questions, you can type in the chat, and I will quickly look at what we can do to improve it a little bit. I know that we can definitely improve the encoder and decoder, and some of you who did the homework, you can definitely make it much more powerful. But I also want to check if we could do something with regards to model by adding some kind of constraints, because I had a lot of things with the models. I'll check my repo that I made for these models. So So the epsilon will produce something in main part of -3 to 3, because that is the standard deviation of 1. Then the sigma and the mu. Okay, so there could be some constraints, like for example adding some sigmoid, but I don't want to like just to overdo this a little too much. So there's a lot of things you can research. You can try to change the priors. You can try to add some constraints here, for example sigmoids and stuff like that, or 10H, but not sure. Like I think the 10H would not be that beneficial in this case. So okay, the decoder part. Okay, so torch and convolution to the transpose. Of course, we want to go the other way. So I'm not sure. Double check if this is just a. It might be just the mirror of the encoder. So let me check. So if we had a 16 and 32, now we can just flip to 32, 16. Then the leaky row. Or the relu, it doesn't matter that much. So then the batch norm, now the batch norm to the 16. Then we'll have again the convolutions. So the convolution then is coming from 16 to 16. So maybe again this one. Maybe we can copy just that one. 16 to 16 to 4 to 1. It seems like it is the mirror of the encoder. So then again this part. So there was the from the 16 to, so from the 8 to 16, but we can just copy this line and change 16 to the 8. And here again 8. Here we add the commas, I forgot them. So, like that. We'll double check if you're not screening with some questions. Okay, no questions. that, so I think those were answered before. So 18 to 16, 18 to 6, sorry. 16 to 8, I don't know what I'm talking about. Then 4, 1, 2, this is good. Again, the non-changing one, I guess there is one, 8. So it's not really non-changing because the width and height is changing, but just the channels are not changing. So the 887, need to be careful by copying these things, not messing it up. So then 8 to 4, so I'll find that line. Here is the line. Copy this line, go down here, copy this line. 8, 4, just a reminder, if you would like to make like state-of-the-art model, you should use the what was the name? Bilinear upsampling and all sorts of upsamplings, not the transposed convolutions. Transposed convolutions create a checkerboard that is not so fun. So 8, then 4, then from 4 to 1. So there is another one. So, and here we'll have at the end sigmoid. Sigmoid. And here we'll have the 4 to 1. 4 to 1 and kernel size of 5. And I will need to check if this output is proper. So to check this again, we can, to check this, what we can do, we can have the breakpoints here. If I run it, it should work without the error. If there is an error, then that means that some number is wrong. It could very easily be that there is some problem. There are a lot of like numbers that can be, okay, it seems like it might work. So the size, at least it did not crash immediately. So yeah, so 64 batch size, 1 channel, grayscale, 28 by 28. That is the standard size of the MNIST type of datasets. There are extended MNIST, there is usual MNIST, the Japanese MNIST, all sorts of varieties. What you like, you can find. So here, this one is ready. So just to check that you're up to speed, I will ask some questions. So why should we add sigmoid at the end of decoder? So yeah, that's my question. Why should we add the sigmoid at the end of the decoder? What do you think? So if I look around here, yep, that's my question in the chat. So if you're ready with your decoder, or at least catching up with the tasks, then maybe you can answer that one in the chat, and then we'll add the middle part of those encoder mu and encoder sigma and the forward pass. And then we'll need to implement the loss function and we'll be done. So that would be great if we get to the point where we can start training this stuff. So yeah, I will let you complete the decoder and answer my question in the chat, and then we'll continue. Just a friendly reminder, we have a question in the chat about the why should we have the sigmoid at the end of the decoder. So if somebody have ideas, you can answer. If not, then you can type in minus and try to finish your decoders. So I see the first answer from Christopher. He's saying that the sigmoid will smooth out the output values of the decoder of the image that we are producing, basically. But I would like to hear maybe some other opinions. If somebody can think what would happen if we not add this sigmoid at the end, and what is actually our output. So maybe you have some other ideas as well. And I'm looking at the score right now. So we have again two or three people already finished the decoder. So maybe you could answer my question in the chat, at least some ideas, and then we'll move on. So nice. Finally, Everett. So Everett is one of the guys who is doing very well with these workshops. I have never met him, but I'm not sure. Maybe I met him when we had these workshops in person. But still, yeah. So the answer is very simple. So you have the outputs of the range of 0 to 1 as the grayscale pixels, right? And if you don't add the sigmoid at the end, there is nothing stopping for the model to giving back you anything from minus infinity to plus infinity. Of course, the model will try to learn the correct values, but why we should do this job harder? You know, we can do this, make the model life a little bit easier. So yeah, that's one of the things. Then let's start adding those encoders for mu and sigma. They actually are quite simple ones. Just a second. So the encoders for mu and sigma, these are just linear projections. Again, I can repeat that you can add here not only linear projection, but you can have also a sequential model with the hidden layers, right? and that would be also cool. So, but maybe that would even work better in some cases. But here we'll just make the very simple projections. So these ones, this is very simple ones, right? So I will maybe add also these two lines to the Google Jamboard. So if somebody is not following up this quickly enough, so like these are really simple lines. So I think you should understand them. So if we don't do these projections actually with different weights and just use the same value for both of them, then it will not make much sense, but we need to do those projections to actually have two different values for the normal distribution equation. So here then this part, Z sigma, sigma, self encoder forward out flat. So the out flat, just to remind you again, here we have the output batch channel width height. We of course want this to be a batch channel because at this moment after the encoder we will get the batch channel 1,1. Remember we talked about this many times, that you can change dimensions without affecting the data, of course. So here B to C, and here we pass to the Z sigma, Z sigma and Z mu. Very simple stuff, Z mu. And now the thing that you have not done yet, so with regards to probability distributions, you can sample them, of course. So if you have a function that is for the probability distribution of the normal distribution is the equation that I gave you in the slides. So there is no, you could actually sample from that equation, but there is already one made for you. So there's a mean around 0 and standard deviation around 1 as it was in this slide, and also the size should match the Z mu size. And also we want to move this to device so we can run it on Google Colab and GPU, because of course this is a new vector and this must be on the same device as the all other vectors, right? So otherwise we cannot do the mathematics with it. So here, and then this small, very simple but very significant equation that is called Reparameterization Trick. So Z sigma by Hammond product by the epsilon here, and then this is like a pairwise multiplication, basically very simple stuff. And now we have this part ready, I think. So I will also add this one to the Jamboard. And if you scroll down, I will not do this now just to not interrupt people working on this code, but if you scroll down, you will see that the loss function is missing. And I believe that by the knowledge that you have right now, you must be able to implement the loss function yourself. So I open right now the task 14.4, where you need to implement the loss function and submit your task basically. And meanwhile, I will run this in Google Colab, and then I will decide if I show the loss function in the live session or not show it, because you should be able to do this because it's really not hard. And I just want to motivate you to do this yourself and not just copy it from me. So I will go to my Google Colab stuff and run the experiment so I can show you how it trains actually. And I might not show today the loss function before you because I want you to implement it yourself. So I believe that you can do it yourself. So let me see. So yeah, The one thing that I also want to emphasize is here up inside we have the include classes. So we are including only 4 classes of all of the possible classes in the MNIST dataset. That is 10 classes. Actually, you could also try to use MNIST. This one is with I think I'm not sure, like 32 plus letters classes. So and the idea is that we use only 4 so that the training is much faster, but you could try it with all of them. So if you use only those 4 ones, let me show you what will be the results if you implement the loss function correctly. If you don't implement the loss function correctly, you will probably not get the results that I will show you, but I hope that you will do this correctly, because we have done so many loss functions. By this time, you must be able to do this yourself. So, and I give you the equations, so this is really, really simple stuff. So, and the hard stuff we already just did with regards to reparameterization. So if you look, so this is a trained model on the Jamboard. The nice cats are walking up there. You know how to enable them, right? So see the very beginning with my default parameters that I gave you with the script, you get that the output is always very similar, right? So if you enforce your KL even stronger, if you give the KL value, let's say 0.05 or something, it will be stronger. All of these outputs in the beginning will be even more the same. So after the first epoch, you see a little difference. So the zeros are a little bit different than the other numbers. And then, so this is again, I think, only 4 types of classes or 3 types of classes. So now all of the losses are going down, but the outputs are not becoming much better. And then at one moment you see something beautiful. The KL is starting to rise. And as the KL starts to rise, the output is starting to get better. And then there is this dichotomy. You need to find what is the KL value that is kind of enforcing the distribution enough, but at the same time releasing through enough information so that you get these numbers in some kind of visible shape that is reasonable. So let us see. So if we go down to the 58th epoch, you already see that the outputs are quite reasonable, but now the KL is quite huge already. So the better situation would be that KL starts going again down. Maybe the KL is too weak right now, so maybe I can rerun it a little bit with the stronger KL. So let me see. So if I go back to the code for a second, I don't want to show you loss function, so I'll also show you how to change. So here are the hyperparameters. I gave you already some that are working fine. Maybe you can add the noise. That might help, because the denoising autoencoders are always a little bit stronger. But the beta is maybe too weak. It seems like it's a little bit too weak. Maybe we can change it to 0.05. And if I run it again, then we'll hopefully see something interesting. So if I go back to the code, let's check that there is no more questions, and let me see if nobody yet implemented the loss function, but it is really not hard. So let me go down to show the loss function part. So here we have all of the variables that you need for the loss function. We have this part already done, right? And this one. So just a little hint. So the little hint is that you will need to have the loss as a composite of these 2 parts, right? And then you implement the middle parts. That is really easy stuff. So hopefully somebody will do this tonight. So yes, one person already did this. I hope that if you run this on the GPU with the Google Colab, you will start seeing these really interesting results. and you can start discovering and playing with the hyperparameters, with increasing the dataset, with changing the dataset, with changing the encoders, decoders. So there's a lot of things you can try out and get really interesting results. So I can show you immediately that after I increased the KL factor, so that KL is now 0.05, I see that immediately the outputs look all the same. So the KL is much stronger now, 5 times stronger. So it will take a lot more time for the KL to break out. So basically it kind of pushed the KL to the moment that the only way how you can proceed is increasing the KL so that the the reconstruction loss would reduce. But I'm not sure, maybe I went too far, maybe I killed it, because 0.05 with this kind of weak encoder and decoder might be too much already. Not sure. If it will be too much, I need to reduce it a little bit, maybe to 0.02. So this is a balance that you can find, but I showed you before that this is working, so it's possible to do this. So yeah, so that's it for today, basically. I hope that you will get your variational autoencoders working. If for some reason you're not able to implement loss function, then you need to, I don't know, like ask me in some manner, write me some questions, or you know my contacts, or we can set up the meetings for the research. So it seems like maybe I went too far now with using the 0.05, but I don't know, like it could be that the optimizer will start getting it out at some moment in like in epochs later, but it seems like it's too strong right now. Let me try to change it. So if I try to use it now as a 0.02, so let's see what will happen with this one. So 0.02. I don't really want to kill it that fast. Also, I am using only those, let me check how many classes I'm using. I'm using only 4 classes. That is really low number. So maybe you should increase the number of classes that you use. That will also give some variability there. Okay, it seems like all of these are the same. Hopefully it will not be killed. Let's see. So this is the first kind of generative model that we have made in these workshops. Hopefully in near future we can make also some GAN. We also, the next time we'll make the UNets, so that's for the semantic segmentation. Then after that we'll make probably RCNN for the instance segmentation with the region proposal network, and then we'll make GAN, hopefully. So yeah, a couple of interesting models ahead. Depending on the progress of some students attending these workshops, maybe we can do also some reinforcement learning, but we'll see. So it seems like the 0.02 also a little bit too strong, but I'm not sure. Like it could happen that at some moment it could go back. It's not sure about that really. Maybe the learning rate is not right. So with these kind of models, these parameters are so picky. Let us see. So maybe we can add the learning rate. So you should do the hyperparameter search as well. So you could try out different hyperparameters, hopefully in automatic manner, not manually. But yeah. So I will do the last test. Maybe it will go with those nice graphs that you've seen before. If not, then we'll end this workshop. But hopefully we'll see something nice now. Not sure. This is a little bit shot in the dark, of course. So this one looks a little bit in good reconstruction, but at the same time, in the very beginning they all should look the same and then start to break out. I also don't want to wait for 20 epochs or 100 epochs, not sure. Okay, I will write in chat, is it working for you? So you can type in plus minus. If there's some question, you can add the question. So now I put KL at 0.02 and the learning rate at E-4. So one person is saying plus. That's nice. That's nice. So another thing that I think for the homework, what I will do, I will give you the model that you can play around with the other end. So the generative part of creating all sorts of interesting like effects when you have trained your model, what you can generate on the other end, like playing with the Z vectors, that would be really fun, I think. So this one is converging very slowly, not sure what will happen. I would like to see KL going up a little bit. That would be nice, but they should be flat in the beginning, and this is going so slow. So I don't want to wait for that. So let's return to the nice pictures that we already have here. So this is what you would ideally would want to see when you find the right hyperparameters. So the hyperparameter search is something that you always should do. You can never train your model just with the first try. So you just like pick some random parameters and think you will get the best model. That never happens. So you need to find the ones that would produce something like this. The homework model, I think, will be something like this as well, where you have the KL going up and then going again down. That would be ideal position. Also, let me check one thing. The last thing before we leave is that some time ago, recently I think, I made a model for like one of the state-of-the-art variational autoencoders that you have, and I published it in the GitHub. So let me share only that one. So you can find it in GitHub, CC beta variational autoencoder. So that was my repo, Torch CC beta variational autoencoder. Funny that not many people have yet found it, but there is, if you read that paper of that autoencoder, of that variational autoencoder, so this is a Torch CCC beta variational autoencoder here, and if you read the paper from which it originally came, this is really powerful idea that you have some compensating factor. So understanding disentangling in beta variational autoencoders, and here there is some moment, there's those pictures that I showed you before, but they introduce the compensation factor here, and this one allows to counteract the KL that is going in the opposite direction. This is really I think a good way to improve your models basically. So this is something you can look at. Okay, so that's it for today. Hopefully these models are quite cool and fun, and you can imagine what you can do with them. And yeah, so keep following what we're doing, and see you next time. Okay, bye bye.